moving on to key features of quadratic functions. This is going to be the notes for 13A. I do have this loaded up as a PDF for you, so you can just fill in the blanks, or if you want to rewrite it all, you can. So the goal of today is to be able to identify quadratic functions, and graph by using roots and end behavior. And the first thing we're going to start off with is a couple definitions. And we've talked about these in class, but I wanted to get a formal definition in your notes. So an independent variable is a variable whose variation does not depend on that of another. And it is a definition, so I suggest you write it in red or highlight it, whatever you've been doing in your notes to keep that consistent. And we've already talked about that this is usually your x values. Our second definition is the dependent variable. The dependent variable is a variable whose value depends on another. And the way I kind of look at these is which one depends on the other. Like your paycheck, so the amount of money you earn, depends on how many hours you work. So I try to word it like that in my head to differentiate between the two. Then we've got domain, and domain is your set of all possible inputs, or in other words, your x values. And then your range is your set of all possible outputs. Which are your y values. So make sure you have those definitions copied down, and then we are going to move to that page in your textbook.
Scene 1, 2, testing 1, 2, 3.
We are going to move to that page in your textbook. So we're going to use page M113. So it's going to be activity 1.3. You're going to go ahead and number that page 13B because it will go in the inside of your folder, in the prongs of your folder. So Maureen and Matthew are designing their backyard patio. There will be an entrance and exit off the front and the back of the patio. The sequence shown represents different designs depending on the size of the patio. So take a look at what's going on in the pictures. And then for number 1, you're asked to analyze each design in the sequence and describe as many patterns as you can. So pause the video, write down anything that you notice about the design, whether it's mathematical or not, because that might help you figure out what's going on. So there's a couple things that I'm going to put down. And if you have something different or if you want to copy mine down, that's fine. I put that there's always an entrance and an exit. That does not change. No matter what, there's an entrance and an exit. So for me, that meant there was always an extra 2 squares being added. And then if I didn't look at the middle 2 square, at the outside squares, only looked at the middle. So if we're talking about the middle section here, middle section, the actual patio, I said in this one, it's a 1 by 3 because it's 1 block tall and 3 blocks long. And then in this second design, it was 2 by, because it was too tall, 1, 2, 3, 4, 2 by 4. And then this was a 3 by 5. And then I took a look at the total number of squares. And in the first design, there's 5. There's 3 in the middle and then 2 on the ends. And then there was 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we had 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And that's all I had. So I did notice that the pattern here for the middle section, that the height goes up by 1. So I would say that this next one would be a 4. And then at the same time, the length also goes up by 1. So 3, 4, 5, we would say that this would be a 4 by 6. And then I went ahead and said that the next would be a 5 by 7 in the middle. So anything like that, just to get your brain thinking about the patterns. Take a look at number 2. Go ahead and sketch design 6 of the sequence. So if this kept going, we'd have design 4, design 5. So then what would design 6 look like? That's what they're asking you to do at the bottom here. So in order to do this, I just kept going with the numbers I had for number 1. So design 1, design 2, design 3, design 4, design 5. So my next would be design 6. So my height of the patio would go up to a 6, and then the length would go up to an 8. So this would be 6 by 8. One, 2, 3, 4, 5, 6. So it stopped there. Then we'd go 1, 2, 3, 4, 5, 6, 7, 8. So the middle section would be 6 by 8. If you wanted to shade that in or whatever you were doing. And then we would have the patio, the entrance here, and the exit over here. So Matthew has 170 tiles he can use for this project. Identify the largest patio design that he can make. Show or explain your reasoning. So see if you can figure out number 3 by yourself. Pause the video, try and give a sketch, whatever you would like to do, and then I will explain it. If you haven't paused the video yet, you need to go ahead and try number 3 by yourself. Okay, so like I noticed before, it didn't matter how big the design got, there was always that entrance and that exit. So I knew that however big this middle section was going to be, I needed 1 tile for the entrance and 1 tile for the exit. So I just took 170 and I subtracted 2 from it because that would be the number of tiles I could use for the middle. So then what I did is I just tried to pick some numbers that got me close to 168. But notice your height and your width have a difference of 2. So let's say I said that my height, my width, that I wanted the height, so this here, to be 10, my length had to be 12, because it always stayed 2 more, and that would only give me 120 tiles. So then I went up to 11 because I knew I had to go bigger than 120. So 11 times 13 was the next thing, because the width had to be 2 more, gave me 143. So then I did 12 tiles, and that would have to be 14 over here. And 12 times 14 gave me 168, and 168 was all I had left. So the dimensions of this patio would be 12 by 14. So let's go ahead and go back to the notes that we've got going on here. And let's fill out this chart. So in design number 1, how many total tiles were there? There were 5. In design 2, there were 10. In design 3, there were 17. In design 4, there were 26. And in design 5, there were 37. And we're looking for some kind of a pattern that we have going on. So from 5 to 10, the pattern was we went up 5, so plus 5. From 10 to 17, it was a plus 7. From 17 to 26, it was a plus 9. And then from 26 to 37, it's plus 11. So if this would have been a linear pattern, this first difference would have been the same, but they're not all the same. So we have to go out further for a pattern. So from 5 to 7, we added 2. From 7 to 9, we added 2. And from 9 to 11, we added 2. So this is the first difference that told you it was linear. If there's a second difference pattern, so a second difference pattern is what tells you that it is quadratic. So let's fill out this graph over here. This is your x-axis and your y-axis. So you have to decide which one's the independent variable. So does the total number of tiles depend on the design number, or does the design number depend on the total number of tiles? The total tiles depends on the design number, which means our y-axis is total tiles, and our x-axis is design number. On the y-axis, we're going to count by 5s. And then down here on the design number, we're just going to count by 1s. And then you're just going to plot your points as accurately as possible. 1 was 5, 2 was 10, 3 was 17, so about halfway between 15 and 20. 4 was 26, so just above the 25. 5 was 37, so just above the 35. And as you can see here, this does have more of a curve to it, even if we weren't the most accurate in graphing our points. So like I said, this is a quadratic, so go ahead and write quadratic function brain dump. And I want you to pause this video and write down anything that you can remember about a quadratic function. And we've already talked about quadratic functions, so you could sneak back into your notes to page 3 and see if there's anything that you can write down from page number 3 that you should have. Okay, so basic stuff from page 3 is it's a parabola, so it can either be shaped up, there's a positive a value, or it can be shaped down if it's a negative a value. And we have talked about standard form already, and there's also 2 other forms of a quadratic. So if you don't have this stuff written down, I would add it. So standard form of a quadratic is y equals ax squared plus bx plus c. And we've talked about that. There's also factored form, which you should have gone over and integrated to. And in factored form, that's y equals a, and then in parentheses, x minus r sub 1. So the 1 is down here like the opposite of an exponent. And then x minus r sub 2. In factored form, and I'm going to put it over here. In factored form, your r1 and your r2 tell you what your roots are. And then the last form is your vertex. So we have vertex form, and that's y equals a, x minus h, and that's squared, plus k. And in vertex form, your h and your k are your vertex. Something else that I wrote down is the quadratic formula, which you should have learned and integrated to. And that's x equals negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. And if you have anything else down there, that's fabulous. Just make sure that you have written down the 3 forms and all of their components. Okay, so onto the back, we're going to talk about end behavior. And end behavior, if you know the basic rule for end behavior, you can make all kinds of assumptions based on the exponent that a function has. So for end behavior in a quadratic, you need to look at the a value, so that first coefficient. And we know if it's a positive a value, it's shaped up like a cup. And I'm going to move over here. And if there's a negative a value, it's shaped down like a frown. And you don't even have to put this on a graph to see what the end behavior would be. As x goes to negative infinity, comma, f of x goes to where? So on the left-hand side, which way does your arrow point? It points up. And if you remember, on the y-axis, if you keep going up, it goes towards positive infinity. Finishing the other side, as x goes to positive infinity, f of x goes to, so on the right-hand side, which way does your arrow point? Also points up towards positive infinity. So it doesn't matter if that first number is a positive 7, a positive 27, a positive 1/2. If that first number, that a value, is positive, this will be your end behavior. The opposite is true for a negative a value. As x goes to negative infinity, so on the left-hand side, your arrow points down, which means your y values go towards negative infinity. And as x goes to positive infinity, so on the right-hand side, your arrows again point down, so f of x also goes to negative infinity. Again, it wouldn't matter if that a value was a negative 1/2, a negative 7, a negative 207. If that first number is negative, it will be shaped down. And we're going to need to know this when it comes to graphing with our end behavior. So, finding roots in factored form. if you are given a quadratic in factored form, you have to know how to find the roots. The very first step is you are going to take that function and set it equal to 0. And then you are going to take each element, so set each element, and you'll see what I mean by element in a second. And set each of those equal to 0. And then you solve for x. So if you're in factored form, you're going to set the equation equal to 0. You're going to set each element equal to 0, and then you're going to solve for x. And we're going to have 2 examples here. Okay, so the example says find the roots. So we have y equals, and then in parentheses, x plus 3 times x plus 1. Your first set of directions is to set that function equal to 0. So instead of the y, we're just going to plug in a 0. Then our second step is to set each element equal to 0. We have 2 what I call elements here. You have this x plus 3 and this x plus 1. So what I do is I just put a line down the middle, and we're going to put x plus 3 equal to 0 and x plus 1 equal to 0. And then you just solve each of those equations for x. So to get x by itself, we would subtract 3 from both sides and get x equals negative 3, subtract 1 from both sides, and get x equals negative 1. So just like I showed you earlier, that this is really x minus r1 and then x minus r2. To find out the roots, you could always just take the opposite of the number in parentheses, if it's a whole number. So this has a plus 1. The opposite of a plus 1 is a minus 1. The opposite of a plus 3 is a negative 3. And why would you take the opposite? Because this is x minus in factored form. If you don't want to remember that, set everything equal to 0 and solve for x. Okay, looking at part B, we want to find the roots, so we are going to set this equal to 0. So 0 equals x, x minus 5, x minus 1. Set each element equal to 0. So I've got a set of parentheses, so I'm going to draw a line there. And we have an x in a parenthesis, so I'm going to split a line there. And you set each single thing equal to 0. So x equals 0, x minus 5 equals 0, x minus 1 equals 0. This is already equal to x, so one of the roots would be x equals 0. X minus 5 equals 0. We would add 5 to both sides and get x equals 5. Add 1 to both sides and get x equals 1. So this function actually has 3 roots. How did you know that without solving for it? This problem has 3 x's, so this would actually be a cubic function. And that cubic would cross the x-axis 3 times. It's that simple, but you have to remember those 3 rules. Now we're going to graph on the other page using roots end-to-end behavior. So the first thing you have to do is you're going to have to find and plot your roots. Then we're going to sketch the end behavior. According to your a value. So what does that mean? If it's a positive a value, then you know your ends are going to be, it's going to go up like a cup, so both of your tails are going to go up. If it's a negative a value, you know that your tails are going to be down. And then third, you're just going to sketch the remaining parts of the graph. And it doesn't have to be perfect. Sometimes you might find it helpful if you find the y-intercept. If you want an extra point to plot. Find y-intercept if you want an extra reference point. And that should finish all of the notes for page 13A. So your front should look like this. Your back should look like this. And your workbook page should be titled 13B, and we only did the front.